Right, in lesson 8, we're going to be talking about something that it already seems really familiar. All of this stuff, you're going to be like, I already know this. But there's one kind of difference in, I guess, the terminology. This is the limits of continuous functions. And on your assignment and on your test, you're going to be dealing with continuous functions and figuring out is something continuous or not. Nothing is going to change as far as what, like, the method that we've been doing limits. But again, it's just kind of keeping in mind that key term, which is continuous. So it's kind of self-explanatory. It says a continuous function is one whose graph has no breaks. So that means not any endpoints. And no endpoints mean that, again, your graph is basically going on to infinity from either side. And we have to have that because we have to have, in order for a limit to exist, it's got to approach the same number from both sides. And if you imagine an endpoint, so if you think of like an endpoint, something like that, well, it's approaching a number from the right side, but it's not approaching anything from the left. So therefore, the limit is not going to exist, which I know is pretty self-explanatory. It makes a lot of sense. It's saying a function y equals f of x is continuous at a point x is equal to a if the function has a value, so it actually exists for that point, the limit as x approaches a exists, and the quantities in 1 and 2 are equal. So again, that's just kind of saying like my point exists, so we have no endpoints, and we also want, so let's say for instance this would not be continuous. Again, because it's a non-permissible value. So no NPVs. Also, that means like no asymptotes. That would not be considered a continuous graph. Again, because there is basically a break in it. Okay, so again, kind of all different situations that you need to be aware of. So number 9 is just saying evaluate the limits for the following continuous functions. Already it's telling us that it's continuous, so we know that our limit is basically going to exist. Now remember what we did in that last lesson. These ones are way simpler than the ones that we've already done because we can literally just plug in our value and get our limit. So I've got 2 times 2 squared minus 2. So 2 times 4 basically is 8 minus 2 is going to leave me with 6. So we know again that again the limit exists and it is going to be continuous. And here the next one, 10 squared minus 10 times 10, well, it's going to be 100 minus 100. Even though it's 0, don't be afraid, it still exists. It's just that the limit is going to be 0. So everything here is pretty self-explanatory. The only thing is you just want to keep in mind that we've got a new word, continuous, and just kind of picture in your mind what that means. Again, no endpoints, no non-permissibles, and no asymptotes. If we look here in number 10, prove that the given limit does not exist. So we want to prove using obviously our table here that it does not exist. Now the table is really, really good to show that limits don't exist. Algebra can be a little bit trickier, and then obviously, I mean, you can look at the graph, but you can't use that as your complete solution. Can't do that. So as the limit, as x is approaching 0, I've got 1 over x. You can see here there is no simplifying that can be done. And when I plug in 1 over 0, we know that that is undefined. So our limit does not exist. So algebraically, that would kind of be the only thing that we could do there, unfortunately, to prove it, which is kind of, I mean, it's not very adequate. So what we can also do is use our table, like what we've been talking about. So we can say we're going to approach approach 0 from the left-hand side and 0 from the right-hand side. And I know a lot of students tend to hate doing these tables, but remember, in case you haven't watched any of the other podcasts, there is a shortcut on how to do this. Just go to the help desk and ask the teacher there, or ask your teacher in class to show you. So x is less than 0, because remember we're coming from the left-hand side first. So we can use, let's say, negative 0.5, negative 0.1, negative 0.01, negative 0.001, so on and so on. And we know all those are approaching 0, which is exactly what we want. Here, I've actually evaluated all of these for us. The magic of virtual classroom podcasts. And you can see, what is this number approaching? -2, -10, -100, -1,000. It's getting huge. So it obviously is going up to, or down, I guess, to -infinity. The next one is 0 from the right. So 0 from the right, my numbers have to be greater than 0. So again, I would just use the same ones, but obviously positives. Okay, we know that that again is approaching 0 just from the other way. And the cool thing is, you're going to notice they're the exact same numbers, but just positives. And so obviously, what is that going to be approaching? Well, it would be positive infinity. So if I wanted to look at the graph of this one, if you guys take a look, either on your calculator, do a table of values, do whatever, you're going to see that this graph looks similar to this. And basically, you know, when x is equal to 0, okay, right here, from the left, we're approaching -infinity, and from the right, we're approaching positive infinity. So this is an excellent way to show, because these two things are not equal, therefore we know our limit does not exist. Okay? Because again, they have to be the same thing. If we do one more example of showing why the limits do not exist, and again, what you guys can do is pause this, make sure that you can show me on your own, and then just double check your answer. We can do this two ways. We can do, obviously, well, we can do it three ways technically. We could do the table of values, we could do graphically, or we could show algebraically. Me personally, I love doing the algebra way. And in this case, we can actually kind of manipulate this to show that even though we're going to factor it, it's still not going to give us an answer. So if I manipulate it, okay, I know obviously this is a PSA 1, right? So the factors of 2 that add to 3. So we're going to get x plus 2 and x plus 1 over, this guy is our difference of squares. So that's going to be x plus 2 and x minus 2. So this is nice. We can cancel these guys out, but unfortunately, we're still left with x minus 2 in the bottom. And there's no more simplifying that we can do here. So therefore, okay, if I plug that in, 2 plus 1 over 2 minus 2, 3 over 0 does not exist. So algebraically, that's a great way of showing that the limit does not exist. For those visual learners out there, which I love, graphically, don't forget that you can always do a table of values and plot your points out. Don't just want to plug it in your calculator. If we look at this graph, basically we know, according to the graph, we've kind of got an asymptote right at x is equal to 2. And our graph is going like this and like this. And you're actually going to notice at 2, we've got a little hole in that graph there as well. Oops. Okay. But again, we're looking to see what's happening when x is equal to 2. Well, obviously, this one here is going to -infinity. This one's going to positive infinity. So very similar to that other question that we did. It's obviously not going to exist because they're not approaching that same number. So guys, as always, don't forget to practice. You got page 27 here. Do a couple of those questions, and then we're going to be finishing this up in a couple more lessons.